is this? Selection. Now we're going to solve the second part. And the second part of the exercise says this. The instruction, after assigning each student a topic, the instruction must draft a schedule for the order of the 30 presentations, right? So let's try to kind of go to our toolbox and see what is this asking? And in the end of the day, this is the kind of selection without replacement exercise, or what we call this particular case, it's a permutation, okay? So this is what happens. You have 30 students, so this is student 1, 2, 3, 4, up until 30. And each one has a theme, right? So you have, this is student 1 with team 3, for example. This is with student 2 with team 4, team 1. It doesn't matter. You assigned, right? You assign something for each student, right? And what you want to do is ask the students to come forward, right? Or if you think about a line, you could line up the students in a sequence of presentations they will do, okay? So let me do it this better. I'm going to do like this. So you have 30 students and you're going to position them in a line with the first presentation to the 30th presentation. And you're going to do, okay, come the first student, come the second student. So let's say Louisa, Sarah, Thea, Michael, Brian, right? And so on, okay? Terry, I don't know, lots of people, Daniel. So in the end of the day, what are you, if you choose different sequences, what are you thinking about? A shuffling, right? It's an order shuffling in 30 bins. If you have 30 bins, you're kind of choosing what goes, which people, who goes in the bin, right? And you can shuffle it. You can kind of change the order. When we talk about order, when we talk about shuffling, we're talking about permutation. So for example, if I selected Louisa first, in my second decision, for my second position, I can't select Louisa anymore, right? Because Louisa is gone. Louisa is already, she presented. I presented, right? So this is the kind of exercise where each layer of decision, you lose 1 degree, right? You lose 1 unit. So if I had, for the first place, for the first presentation, if I had 30 options, for the second presentation, I would have 29 options. And what about the third? 28. And up until 1. Why? Because I have the same number of bins, right? I have 30 bins with 30 people to choose. So I go up into 1. This is kind of a shuffling thing. If you think about the different options I could have chosen S, L, T. So whatever I'm doing, whatever option I'm taking, I'm kind of, if I consider all the options, I'm considering all the options that I have by shuffling everyone, okay? So in the end of the day, this part of the exercise is 30 factorial. And the final answer of this exercise is that how many ways, so the exercise asks like this. Sorry. So in how many different ways this can be accomplished? This is the final question. So, in how many ways this can be accomplished? Well, this can be accomplished in, you think about the 2 tasks, right? The first task was 4 to the 30th, right? This was the first task. It's 4 to the 30th. But then I will do a subsequent decision. I'm going to do a subsequent task, which is shuffle everyone. Okay, so this is times 30 factorial. This is the final answer. It's a lot. Okay, it's really, really, really a lot of possibilities. Okay, cool. And I mean, this is a lot, but something that helps, that I think that helps while you're studying for the test or while you're doing the test, you're writing the test, is if you're really in doubt of what you're doing, kind of pose the same example like smaller. So think about this. You could have 3 options of teams, right? And 3 students. Okay? So then you would assign, so you create a bin for Louisa, a bin for Sarah, a bin for Thea, and then you kind of say, okay, how many options I have? I have 3 times 3 times 3, right? Or you could even use 2 if you want to do a smaller example. 2 times 2 times 2. Let's do it in a smaller example. 2 times 2 times 2. Okay, so I have 8 possibilities. Now, how can I, after I assign, what can I do with these people to choose the sequence? Well, it could be Louisa first, Sarah, and Thea. Then it could be Louisa, Thea, and Sarah. Then it could be Thea, Louisa, and Sarah. Thea, Sarah, and Louisa. Sarah, Thea, Louisa. Sarah, Louisa, Thea. Right? I mean, you can count 1, 2. Oh, I think this is just a shuffling. So I think I'm in the right path. This is a selection without replacement after a permutation, a shuffling. So break your problem into steps. The first step is assignment or selection, and all the options can be used, right? Then shuffle it and take this minor example and then just substitute for your numbers, which are 4 options and 30 bins, right? So then you will have 4 to the 30th bin, to the 30 bin times a shuffling of 30 factorial. Okay? So this is something that you can do like in a side note if you're really struggling to understand the steps and find the tool, right? But in the end of the day, everything that we do is finding the right tool, okay? Breaking the problem and finding the right tool. Questions about permutation? No? Good? All right, so permutation is always like this shuffling or sequence or position different objects, okay? All right, so but selection without replacement has permutation and also has a general selection without replacement, okay? So permutation is when you're shuffling or if your number of things to choose is actually equal to the number of bins or positions that you're kind of putting the things on. And the general selection with replacement is just like, generally you don't have necessarily a shuffling. You just have a selection because you have less bins. So for example, this here, the second one, is an example of a general selection with replacement. Okay? So here's the problem. We have 16 swimmers competing in a national competition. A medal will be awarded to each of the fastest 3 swimmers. Okay? So I will give 3 medals. I will give the gold medal for the first place, the silver medal for the second place, and the bronze medal for the third place. Okay? This was an exercise on last year's midterm one. Okay? So think about this. What tools do we know up until now? We know sets. No, I don't think this has nothing to do with sets. Then we saw, let me go back. Then we saw the multiplication rule. Yeah, I mean, there are a sequence of actions. I will have to first kind of select the first swimmer to give them the golden medal. Okay, yeah, I think I will multiply things up. And what kind of rule in the multiplication rule we're using? We're using selection without replacement, meaning that think always about bins or about classifiers or boxes, and think about having your gold box, your silver box, and your bronze box, right? And what you have to do is from this 16 swimmers, okay, I have to pick one to be my golden guy, right? My champion, my golden medal. How many options I have? I mean, factually, it will happen. Like the first one will get there and you will give that person. But I want to know how many possibilities, right? So if you think about all the 16 can kind of get there first, right? So all the possibilities that I have means that I have 16 people, right, that are kind of eligible for getting the golden medal. Or I could select from this 16 people. After I gave the golden medal to someone, I have to kind of select the second person, right? Or if you think about the whole possibilities, one will get there first, and everyone can, and everyone minus the one that got golden can get silver, right? So in the end of the day, how many people can get silver? 15. Okay. Now, as my third action, what I'm going to do, I'm going to select my bronze. Or how many people are eligible to get bronze? 14. So this is a selection without replacement, but it's not a permutation because I'm not taking the 16 swimmers and just shuffling the positions, right? I have only 3 bins. And I'm just selecting. So the general selecting is just a selection where you lose degrees of freedom on each multiplication layer or on each bin. And when I'm talking about permutation is I could say, all right, I want to place all the swimmers on, let's say I'm hypothetically creating this now, but I want to position all the swimmers in a sequence, right? Then I would have 30 in a line. So then I would have 30 bins, and I will have 30, 29, 16, 15, 14, 13, 12, and up to 1, meaning that I'm kind of shuffling the order. Yeah.
Just a little bit confused when to do selection with replacement and
without replacement. So think about this. If you choose the first swimmer here, right? When you're choosing your next layer or your next bin, this person is already received the gold medal. You cannot give the golden medal and the silver medal to the same person. So your option decreases, right? When your option decreases, you're doing the selection without replacement, right? Now, if I'm telling you, oh, you have 16 swimmers, and each swimmer has to choose between a red tube or the blue, right? So you have options for everybody. It doesn't matter if this first one decided to get blue, the next one will also have 2 options. So you don't decrease your options. Okay? All right, yeah.
So would the second thing you described be with replacement then?
Yes.
Okay, great.
Yes, with replacement. Right? So imagine that the first swimmer chose the blue, and I called the second swimmer, and I said, okay, but what color do you have? I have a pack of lots of, I have everything available there, and the second one comes, I want blue too. They can do that. You don't lose the blue, right? You don't lose one option. Yeah.
So, like, on a class or something, we usually are, so it has like 16, 17, 14.
Yeah. Just that. Okay? So you don't have to work out these numbers. It will be nasty.
So
Yeah.
how do you know when to use a permutation and when not to? What, is
So-
there like a specific word or phrase?
Yeah, usually like you have to think about if you're just the word permutation means like a shuffling. So if you interpret the problem as, oh, now I have to shuffle my options, all my options, right? Here you're not shuffling all your options. You have just 3 people selected, right? So from the 16 you selected 3. If you had to select 16 people, right, you would have, if there were 16 people here, I would be just changing the order, okay? So if you interpret your problem as a shuffling, okay, then you would be doing permutation, yeah.
Yeah, but like if we're shuffling, like is there usually like a phrase that would kind of indicate that, like in the problem? Like is there a way we could say, oh right, so like we're shuffling people around?
Yeah, so for example, let's go back to this here. For example, if you have 30 presentations and you want to schedule the order. So what you interpret with that is that you will have 30 things and you're just shuffling the order, or you're kind of changing the positions within that 30 things.
Okay, so like I was talking about like order or position.
Yeah.
But then like if it's assignment, usually it's more like without the
Usually,
permutation.
yeah, I cannot guarantee
Yeah,
that, you
but-
know, like there's not a rule, like a language rule, but usually you have to interpret the problem to see what tool you would use, okay? So permutations are order shufflings, right? What comes first, second, third, fourth, within 4 things, right? So within 4 things, what comes first, second, third, and fourth, you're kind of just shuffling that, you're changing the order. And selection without replacement is just losing a degree of freedom, not necessarily having all the elements changing order. You're just selecting some from the whole, okay? Yeah. Yeah.
Oh, yeah. So, for example, if all 16 swimmers were to be, like, kind of shuffled around, then would that be 16 factorial?
Yeah, exactly, right? So if you think about like, oh, I gave the medals, right? And where's the problem? It's here. So I gave the medals, and now they're going to the podium, right? They're going to the podium. And I have 2, I have right, left, right, middle, and left podium. And let's say that I can, they're all the same height. There's no taller thing for the golden medal. How can I displace these 3 guys? Right? So it could be the golden, the silver, and the bronze. It could be the silver, the golden, it could be the golden, the bronze, and the silver. It could be the bronze, the silver, the golden, and the bronze, the silver, the bronze, and the golden. Then it could be the bronze, the silver, and golden, and bronze, golden, silver. I'm doing this very fast because I'm kind of used to it, but you have 1, 2, 3, 4, 5, 6 options. This is 3 factorial. So you're doing a shuffling. You're organizing the order, the position of things, right? So first of all, you selected the swimmers, and then I say, okay, now position the swimmers in an order. Who is left, who is middle, who is right. Then you would multiply this by 3 factorial. Okay? If I have these 2 actions.
But if we're just trying to put them into a space and nobody can take that space.
Yeah, that's
Like winning a medal.
yeah.
Okay, then
Okay.
we don't use
Yeah.
permutation, and that would be the answer.
Yeah. Okay. All right. So who asked this? You, right? Yeah. Okay. Good. So here is one of another test, another little exercise that was in midterm 1 last year, and this one is a good one. Okay. Because this one brings us the theme of indistinguishability. We saw that for grouping, we're going to get there, but we saw that we have to kind of correct for when the groups are indistinguishable. But actually, indistinguishability is used even for elements. So let's take a look why. Here is the exercise. In how many different ways can the letters in the word adoption be arranged? Okay, stop there. Stop. What kind of question is this? You have letters of a word, and you want different ways to arrange, right? So the word is adoption. But I can arrange the letters in other order, right? I could do D, A, P, O, T, O, I, N. Dapotoin, right? So I know it's not a word, but it's a way to arrange the letters, right? What is this? Is a permutation, because I'm talking about the order, the way I can arrange things within their bins, okay? All right, so, okay, how many ways can the letters in the word adoption be arranged? Well, let's work on that. But there's an if. If T, letter T, cannot be the last letter in the arrangement. Okay, so they just kind of destroyed our happiness by kind of what they are talking about. Okay, because if it was only the permutation, we would kind of know how to do it, right? But now there's an if condition. I have to think about it. So let's think about together, because this is the typical question that comes in the tests. Let me get this. Oh, I can use here. Okay. So let's think about this. If adoption has 8 letters, right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay? So imagine that the position of the letters are like different 8 bins. Okay? And if I were to choose only the permutations, without the condition, without the constraint of T being the last, without the constraint of T not being the last letter. How could I do that? Well, I would change, it would be a factorial, right? Like 8 factorial. It would be 8, first option. I could choose A, D, O, P, whatever, this 8 letters, okay?
Why did it be 7? Because there's 2 O's.
Yeah, I'll go there, right? So this would be a 8 factorial. I could choose 8. I could choose 7, 6, 5, 4, 3, 2, right? 1. But there's something happening here. Does anyone know what it's kind of happening here as a problem? Because this is not the answer. It would be if we didn't have a specific problem there. Yeah.
It's like a kind of the opposite question.
It's a kind of what? Yes, we will count the opposite. I'm working on the whole options that I had, the permutations. But even the permutation is not right. It's kind of not right, right? What changes? Yeah. So this is, I have two repeated letters. I have two indistinguishable elements. This O and this O. Okay? So, in the end of the day, okay, for example, I start with 8 options, then I go to 7, then I go to 6, then I go to 5, then I go to 4, then I go to 3, and let's say that I'm left, let's say that I chose this. So I'm left with 2 O's for choosing, right? I'm left with 2 O's. I chose A first, D, P, T, I, N, and I'm left with 2 O's. Does it matter if this, I choose like this, or if I shuffle the order? It's the same thing. So in the end of the day, I don't have this 2 times 1, right? I stop here because here it doesn't matter, right? Like it doesn't matter the order. So can you see that I kind of got rid of this 2 times 1 here? So I had 2 times 1 before, but this doesn't exist. I don't have this option. This is 1 times 1. I will have just one option. Put the 2 O's there, okay? Because the word is the same. So in the end of the day, the indistinguishability between elements or set or whatever you're doing, you have to correct. So if you have 2 indistinguishable letters, you would have to divide your factorial by 2 factorial. So when you have indistinguishable elements, you get the number and divide by the number of indistinguishable elements. Right? So k factorial here, where k is the number of repeated elements. Right? So, good, yeah. Mm-hmm.
But we didn't talk about the T at all, like that the T count.
Yeah, sure. So we're just working on the whole. Like if I didn't have any restriction, the answer would be 8 factorial over 2 factorial. Okay? Good. Right. Awesome. Now, there's a constraint. T cannot be the last letter. All right. So let's think about options. 1, 2, 3, 4, 5, 6, 7, 8 letters. You can have T here. You can have T here. You can have T here, right? You can have T here. You could choose T anywhere. If you think about doing manually, you would say, okay, I'm going to choose T here. So I already chose T. Then I'm left with 7 options, with 6 options. And then you would have to do again for the T in the second position, right? In the third position. What is best when you have too many things to do? What is best? To think about the opposite. Meaning that, what if I get all the possible permutations and I take out what I don't want? Right? I don't want a T in the last position. Okay? So if I take all the arrangements and take off the T in the last position, I will be left with what is possible. Okay? So I have the whole. Did everybody understand why I did this choice? It would be very, very, very difficult to do with all the T's, right? I mean, it's possible. It's not that much because you have only 8 positions. But anyways, when you there might be other exercises where it's even more difficult. So think about this. If you take t first, and then you would have all these permutations, and you would have to correct. It will be 7 corrected divided by 2 permutation. Then you would have now the other option where t comes second. It will be 7 over 2 factorial, right? Because that would be, it will be 7 options here, 6, 5, 8 options here, 6, 5, sorry, 7 options here. 7 options here, 6, 5, 4, and then I correct to the double O's, right? I would have to repeat this procedure. Now, if I think about the opposite, I will say, okay, I have the whole permutations. I know that the whole is 8 factorial over 2 factorial, okay? So I'm going to do this. I'm going to do this. So I have the whole minus t in the last position will give me all the possibilities that I want. So the whole is 8 factorial over 2 factorial. Now, I have to account for, I have to remove or subtract from the whole the t in the last position. Let's do that. 1, 2, 3, 4, 5, 6, 7, 8. I am going to fix t here. So I don't have a choice here. Imagine that t comes stamped in my last position. I don't have a choice. I cannot choose anything in this bin. It's already chosen for me. What am I left with? Well, I had 8 letters. Now I'm left with 7, right? So 7 letters, options for the first bin, 6 for the second, 5 for the third, 4 for the fourth, 3, 2, and 1, right? So if I got t out, adoption, I got t out, right? T is already placed. I'm left with A, 1, 2, 3, 4, 5, 6, 7 options, right? Let's say that I took A. A is out. How many is left? 1, 2, 3, 4, 5, 6. I got N. N is out, right? How many? D, 1, 2, 3, 4, 5 with the I here. So I got D. D is out. How many? 4. O, P, I, O. I took O. 1 O is out. Then P. P is out. I is out. O. Right? So these are this is one option. But in the end of the day, I made one option here by my choices just to give you an example that the letters they're getting out of my way. But if you think about you chose A, but you had 7 options. Then you would have 6. Then you would have 5, 4, 3, 2, 1. And the T, it doesn't matter, is stamped there for you. Is this right? What should I have to I have to correct something. Because I'm still left with 2 O's, right? What should I do? Divide by 2 factorial. Don't forget the 2 factorial. So I have to divide. So I'll take 7 factorial, and I have to eliminate the 2 O's, right? So it's 7 factorial over 2 factorial. This is the answer. I have the whole permutation, and I'm removing the instances where t goes in the end, right? So I'm fixing the last position. the t last position, I'm fixing it. I'm permutating the rest, right, of the options that I have, and correcting for the indistinguishable O's. Yeah.
I'm kind of confused. I know
Yeah.
if we're not supposed to have T in the last position, why do we stamp it to that end?
Because I'm calculating this, the t in the last position, so that I remove from all the possibilities. So I'm doing the counting the opposite strategy, okay?
How did we get 7 factorial? Do you just like subtract the letter that you're like disregarding?
Yes, so this is what I'm showing you. If you stamp the letter here, you don't have a decision to make in that particular bin, right? And one of your letters is gone. So you don't have 8 letters to do a factorial anymore. You have 7 letters to do a factorial.
So like if we were ignoring T and P, it would be 6/2. That
Yeah.
word. Okay, I got it. Thank you.
Yeah, exactly. You got it. Yeah.
Would you like us to leave it just like that?
Just like that.
Don't go any further?
Yeah. Don't do anything. Yeah. Okay. Other questions? Good? Yep.
Can we do the final answer is 7 factorial over 2 factorial?
No, the final answer is 8 factorial over 2 factorial minus 7 factorial over 2 factorial.
Like you leave it like that?
You leave it like that. Okay, you don't need to work the factorials out. Just leave it like that. Okay? Oh, I have actually a disclaimer to make. In this exercise here of the swimmers, where you're doing just a selection, it might be that your answer, your multiple choice answer, will be in this form here. Okay? Because that's equal. Yeah. Yeah? So if you think about 16 factorial, 16 times 15 times 13, 12, and so on, right? Up until 1, right? What is this? Oh, I missed 14. 14, sorry, 13, 12 up until 1. What is this? 13 factorial. So if I get 16 factorial and divide by 13 factorial, do you agree that this will die? And I will be left with 16 times 15 times 14? Oh, yeah, right? So this might be in your test. So it might be that in your answer, your multiple choices, you won't have 16 times 15 times 14. Actually, you will have the 16 factorial over the 13 factorial. Okay? Good? Eyes. There's some faces like, no. Yeah, I can, yeah.
Like in any question we were doing like this, if we just said, for example, like 16 times 15 times 14, or like whatever other number it was, so like 10 times 9 times 8, like it would be divided by like 1 less factorial than like the last number.
Yeah,
Okay.
exactly. You got it. So I will do a new slide here just so that we have this as this will be on the website so that you can see it later. Every time you have just a selection that's dropping, right? 16, let's say 30, 29, 28, 27, right? I selected 4 things within 30, right? Without repetition. So for the first thing, I had 30 options. For the second thing, 29, 28, 27. This is equal to, take all the factorial, the first number factorial, and divide by the one that's missing here. this is the same. This is the rule. Why? Well, because 30 factorial is this, up until 1. And 26 factorial is this, up until 1. Meaning that you truncate here. Okay, so you divide by the number you want to get rid of, by the part of the number you want to get rid of. Yeah.
So then does it just make most sense for us to start writing those, like the second option? If it's what's
Yeah, I mean, you will see that in the test. I saw the test yesterday. I don't remember if we have exactly this, but for example, in the last year, we had more than 2 questions that had selection without replacement with different notations. Like there was an answer 16 times 15 times 14, which was the swimmer question. And there was another question, if you take a look at the test, it's in the website, that is, it's 7, I think it's 29 over 27 factorial. Meaning that this is 29 times 28. It would be 27 up until 1 here, but you're dividing, you're getting rid of, so you truncate you going down. Okay? So you might find different ways to kind of pose your answer. Okay? If you're doing the open questions, you can leave it either way. Okay? You don't have to kind of adopt a single way. We will understand. But in the multiple questions, you will have to know that both things, they are the same. Okay? Cool? All right. So now, oops, this repeated. This is repeated. Okay. This is another exercise on selection without replacement. Okay? And this exercise kinds of mixes everything. You have to select, and then from the selection you have to permutate. So let's take a look at it. This guy, Ephraim, has a collection of antique watches that he likes to display on the mantle above his fireplace. Ephraim has 5 different Longines watches. So I have L1, L2, L3, L4, L5. They're different between themselves, right? 3 Zenith watches, Z1, Z2, Z3. 8 different Rolex, R1, R2, R3, R4, R5, R6, R7, R8. And 6 different Cartiers, C1, C2, C3, C4, C5, C6. Meaning that Ephraim is rich, right? if he has all these watches. All right. Okay, so in how many different ways can Ephraim line up these watches? Right? Okay, stop there. I know that there's more question to come, but if he wants to line up things, right? How many ways I have to line up things? What is this? Like a permutation, because in the end of the day, all the different ways you line up things are just how the things are shuffling, right? Okay. So this would be the like the permutation things, but there's a situation here, right? It would be very nice if it was that was the question, but it's never that. So how many ways he can line up the watches if he wants the same brand to be kept together? All right. So every time you read a problem, you have to think about the problem the way you were doing it. Remember, we learned simple. We have a few tools in our toolkit. Sets not related. You already know this is permutation, selection. We are in this world where you have positions, bins, choices. So how would you do if you were Efrain, right? How would you do to put the watches there? I will give you an idea on how to think about that. Think about bins, right, or positions. Think about this. If he wants all the watches of one brand to be connected, to be close to each other, together, I would take a big bin or a big box here for the Longines. I will take another big box for the Zenith. I will take a large box for the Rolex. And I also would take a large box for Cartier watches. Okay? It wasn't meant to be different. They were meant to be the same size. Okay? Anyways. But big boxes that feel like it can fit all the Longines, all the Zeniths, all the Rolex, and all the Cartiers. Okay? So within the Longines box, how many Longines that I have? 5. So I would say, okay, there's position 1, 2, 3, 4, and 5, right? So let's focus on this first big bin. How many ways can I position or can I shuffle 5 things within this big box? 5 factorial. Perfect. So within the box, imagine that I have my first box here. I have 5 factorial ways that I could put L1, L2, L3, or L5, or I could start with L5 and then L3. Well, I have 5 factorials way. Okay? Now let's move on to the second bin, the big bin of zeniths. How many zeniths I have? 3. How many ways can I shuffle? Well, 3 factorial, 6, right? It could be zenith 1, zenith 2, zenith 3, or zenith 3, zenith 2, zenith 1, zenith 1, hello, right? All this combination, all this permutations. Okay. What about the Rolexes? 8 factorials, because I have 1, 2, 3, 4, 5, 6, 7, 8 positions, right? I have 8 positions. And I want to shuffle, I want to shuffle the order, meaning I have 8 factorial ways to kind of do Rolex 7, Rolex 5, Rolex 3, and then I choose, right? I have lots of combinations. And finally, I have the Cartier options, which are 6, 4, 5, 6, meaning I have 6 factorial. Cool, right? Is this the answer? No. Why? Why?
Because we have 4 different ways to order.
Yeah, there you go. So nobody told me that the Longines have to come in the first position, right? So I can take these big boxes and I can shuffle the big boxes, right? So the big box, how many ways can I shuffle the big boxes? 4 factorial. So the answer will be 5 factorial, 3 factorial, 8 factorial, 6 factorial, 4 factorial. So where this 4 factorial is the permutation of the big bins, Yeah.
Does it matter what order we write that
No.
as long as we include the 4?
No, it doesn't. And for example, here in the test, I'll show you. This is last year's test. You have access to it. Look at the answer. It's totally out of order. Okay? It's totally out of order. You have to know that the order doesn't matter. Okay? Yeah. You raise your hand?
Yeah.
Mm-hmm.
Like, why wouldn't it be over top of 4 factorial? Like, why wouldn't it be like a fraction? Because you have like the boxes.
Yeah.
You have like the bigger, like you have like the watches inside of each box, and then you have like the bigger boxes. Wouldn't it be kind of like a fraction in a sense? Like
Like a multinomial.
yeah.
So this is not a grouping. We're gonna see grouping right now. Like the next slide is about grouping, because it's not that when you have groups, let's say that you want to select all the watches that are from the Longines brand, right? When you say, oh, I want to group these watches, it doesn't matter to you if L1 comes first, L2 second, L5 third. You just want to keep them. It doesn't matter the order, right? But this is not the question. The question is how to put them in a line. So actually, the order of the Longines will matter. So it's not a grouping, it's a selection, right? So within the Longines, the position of each Longines matter. When I'm grouping, and this is the next slide, I don't care. It could be L1, L2, L3, L5, L4. It could be L2, L3, L4, L5. It could be whatever sequence you choose, you are okay with. So then you kind of divide, because you're overcounting all of these different orders, right? Okay, but we're gonna go there. Yeah.
But if the order doesn't matter, why do we have 5 factorial? Because wouldn't 5 factorial?
No, the order here. The order matters.
1 through 5.
Yes, I want to dispose them in the line. So the order matters. I could have the blue Longines, the red Longines, and the yellow Longines, and the, I don't know. So if I shuffle the order, the line will be different. Right? So if the order matters, that's selection. You're in the permutation selection with a replacement world. Okay? There's no fraction other than correcting for indistinguishable elements, right? But in this case, all the elements are indistinguishable. They're different watches, okay? Oh, before going to group, we're keeping inside the world of permutation. There's another type of permutation that we saw. And it's the circular permutation. Now we're going to go back to groups and talk about groups. So let's what we learned about permutation, a circular permutation. If you have n elements, you want to dispose them. You want to shuffle the order. Number of ways you can put them in order, but circularly, like this. Do you have n factorial? No, you have n minus 1 factorial. Okay? And this is a rule. Every time you're disposing, you're arranging things, you're shuffling the order of things in a circular fashion, subtract 1 element, because there's the thing about the fixed coordinate or whatever. You have to sit one element has to be positioned first and everything, okay? All right, so to celebrate their hockey team's recent victory, the 14 members of the Firehawks are going out to a pizza dinner. So, okay. 14. So I have 14 elements, 14 people. Okay. They are going all to sit down around a large circular table to eat. Well, when you do that, when you hear circular in the test, your brain should go to circular permutation, but that's because that's the only thing about circular things that we saw, right? So circular permutations. All right, so and the question is, how many ways can they be set down? Oh, stop there. How many ways? So how can I shuffle all these 14 people to sit down, right? Well, if that was the question, what would be the answer? 30 factorial. Okay. Is that the question? No, it never is that easy, but let's think about it. So what we have is 5 players, the 5 first players that are waiting to sit. They're lined up to sit in the circular thing. These 5 guys, or let's think about the 5 guys that are related. They're cousins. I don't know. They want to sit together. They want to sit one, they want to stay in a block. Okay? So how many ways can how many ways can I organize these people if I'm positioning 5 of them? So let's think about this. The first, other than having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Other than having 14 chairs, right? I'm gonna kind of stitch the chairs together. I other than have 14 bins, I will think about this 5 people as a one single bin, right? Okay? So think about this. Glue all the 5 people. They're glued together. Sit them first. Right? Because someone has to sit first. Sit them first because they're like, that they want to sit together, so that's the condition. You start and sit them first. Okay? How many people are left to seat? If I position the 5 guys first. 5 guys first, seated. Then what did I do? How many bins are left? 9 bins, right? Okay. How can I position 9 bins, right? Actually, sorry. How many bins I have to position? Well, there were 10, right? But I've seated one first, so 10 minus 1, 9 bins, 9 factorial, okay? So 10 bins left in total, or let me do this, 10 bins, 10 bins, 10 bins in total. So I had this first bin, and I have the other 9 here, okay? Because I have 10 bins in total, and I seated one first, this is the rule for circular permutation, I'm left with n minus 1, okay? So 10 minus 1 factorial, which is left with 9 factorial, okay? Yeah.
So like circular permutations questions, will there always be like that thing where you treat like a certain number of people
Oh,
as,
yeah.
like, one block?
Not always. If you take a look at the previous midterms, you have different questions on kind of, maybe 2 people want to sit down together, maybe 2 people want to sit across of each other. So there are different kind of ways. It's good to look. You have to know how to do it. So my suggestion is go to the past midterms. Try to go through the midterm positioning what tool would you use, and there's the solution. So there's the explanation, and you will kind of get a sense of what tool to use. Okay. Now, is this the answer? Why? Let's see who gets the. So I have 10 bins. That's right. Because it's a circular permutation, it's 10 minus 1, because 1 is seated first, so that's 9 factorial. What do I have to think about still? Ooh.
Like how the 5 players can be arranged?
Exactly. Right? Exactly. Now, the 5 guys are glued together, right? They're not. Think about it. They're not. You will glue them together as a choice, but if you think about all the choices that you had, right? You could have selected 1, 2, 3, 4, 5. I could select you in the chair to the left, you to the second chair, you to the third chair, you to the fourth chair, and so on. So I'm left with how many permutations? 5. Okay, so this is the answer. Because within this line of chairs, now it's a linear. Within this line of chairs, I'm permutating 5 people. Yeah.
So it would just be 5 factorial because like with just their group, like we don't think that it's circular.
Yeah, it's not circular, right? They are like think about 5 chairs, one in sequence of the other, right? They will kind of arc. You'll have an arc of circular thing, but it's not totally. You're not distributing 5 in the circle, right? It's just an arc of the circle. Okay. All right. I won't have time to go into groupings still, but next lecture we will do groupings, and then we're done with the recap. And then we're going to start probability next lecture as well. So I'm going to do this last 3 exercises, and then we're going to start probability. Okay? So, all right. Thank you, guys. Thank you so much. I have to start because we don't have time to do all the exercises until midterm 1. So I have to start. But with this recap, it's recorded in OWL, and you have the last tests. I really suggest that you go through the last midterms. Like the test is always that, that style, the same kinds of questions. So get 2 or 3 midterms, and go through all the solutions, thinking about the tools you would use. Okay.